So today we're going to continue our discussion on cryptography schemes before we move on to the quantum part. So we're going to look at two schemes. Remember, in our previous lecture we first of all came up with the idea of this one pad scheme in which a key was generated and the key was shared between Alice and Bob. But sharing the key opens up the possibility of an eavesdropper picking up on the key and impersonating to Bob that I am Alice or I am Bob. So this impersonation can also take place. So the key becomes vulnerable in the one pad scheme. But then I came up with this other idea of having a box which has one lock and the message is put in that box, and that box is then shared with the second party. The second party inserts his own lock and the box then gets back to Alice. Alice opens her lock and finally the box goes to Bob again, and the Bob unlocks the box with his own lock and reads the message. So we're going to look at a scheme that actually implements this. And that scheme is due to two individuals, Diffie and Hellman. We're going to look at Diffie and Hellman's crypto scheme. But before that, a quick recap of what we looked at in the previous lecture: the primitive roots mod a prime number p. So let's redefine our primitive roots mod p, which we labeled as G in the previous lecture. So suppose p is a prime number and G is a primitive root mod p. It will be a primitive root mod p if for A greater than or equal to 1 and less than or equal to p minus 1, G raised power A generates all distinct numbers between 1 and p minus 1. This is how we define a primitive root mod p. For example, so let's look at a few examples. Suppose I pick up a prime number, say 13. I want to find a primitive roots mod 13. First of all, I need to know how many primitive roots exist. The number of primitive roots of a prime number is given by an Euler phi function denoted by phi of p minus 1. Alright, so if my prime number were 13, then I would need to find the Euler phi function of the number 12. This will give me the number of primitive roots mod 13. Okay, so let's find out this function. So you can use some online kind of calculator, and I'll use Mathematica here to find these primitive roots of 13. And first of all, I need to find out the number of primitive roots, which is given by the Euler phi function. So let's open up Mathematica here. All of this could be done quite easily in a calculator of your choice. up. So I open a new notebook, increase size a little bit. So I need to find the Euler phi function of the number 1 less than the prime. The prime is 13, so I find out the Euler phi function of 12. I'll get the number of primitive roots mod 13. So this number is 4. So there will be 4 primitive roots mod 13. The Euler phi function is defined as the number of integers less than this 12 which are co-prime with 12. But those numbers are not necessarily the primitive roots of mod 13. Okay, so the primitive roots of 13, I need 4 of them, and this calculator could help me find those roots. So now I find the primitive roots mod 13, and those 4 roots are 2, 6, 7 and 11. These are my G's. These are not co-prime with 12. These are the primitive roots mod 13. And if I pick any one of these numbers, so let's pick any one of these numbers. So let's move to the blackboard first. I'm going to describe this Diffie-Hellman scheme, but in order to describe that, I need to have this background in front of me. So my primitive roots of mod 13 are 2, 6, 7 and 11. So let's pick any one of these numbers. Let's pick up 7 and see if it is indeed a primitive root mod 13 by dint of our definition that's given over here. So if I take G equals 7, let me exponentiate this 7 by A, where A varies from 1 to p minus 1. So let's make a table. So 7 raised to power 1, 7 raised to power 2, 7 raised to power 3, 7 raised to power 4, 7 raised to power 5, 7 raised to power 6, 7 raised to power 7, 7 raised to power 8, 7 raised to power 9, 7 raised to power 10, 7 raised to power 11, 7 raised to power 12. So my G is 7, okay, and my A goes from 1 to p minus 1. And I'm going to write all of these numbers mod 13. Okay, so I'm using modular arithmetic. Okay, so of course this gives me 1. 7 raised to power 1 mod 13 is, sorry, 7. So this is 7. This we know is, in our previous lightning fast introduction to number theory, we noticed that if I have a number A which is co-prime with the, of course this is number, every number is co-prime with the prime, and if I take the prime, subtract from it 1, then A raised to power p minus 1 is congruent to 1 mod of p. Right? So this is just a corollary of the Fermat's-Little theorem. Okay, this is Fermat's-Little theorem. And we know that for a prime number, the Euler f phi function for a prime number is p minus 1. That's why this will give me 1. Okay, all of these numbers have to be computed in modulo 13. So let's use Mathematica to compute these numbers. And let's see if all the 12 numbers that I get here, they are distinct and they cover the entire span from 1 to 12. So I make a table, 7 raised to power some a, and I want to do this modulo 13, so mod 13, and my a goes from 1 to 12, right? So these are all the powers of a, the exponents of 7 of g, sorry. So if I put 13 here, the next number is going to repeat itself. So the period of this function, or the order of this function, is p minus 1 as well. Okay, so the numbers are here 7. Can you please speak them up? 10, 5, 9, 2 and more, right? So everything is mod 13. Keep that in mind. So all of these numbers are distinct, and they span from 1 to 12, which is 1 less than the prime number p. That's why g is a primitive root modulo 13. I can pick any one of these g's. I can pick 2, I can pick 6, I can pick 7, 11. Let's see what happens if you pick 6. Do I get all 12 distinct numbers? Yes, I do. Alright, so these 12 numbers are all distinct. They cover the entire span from 1 to 12. So there are 4 primitive roots mod 13, the 4 g's, and I can pick any one of them. Now how does the algorithm, the Diffie-Hellman algorithm work? So let me just close down this thing. So the algorithm works thus. So I have Alice. Alice's world, Bob's world. Okay. Both Alice and Bob decide a prime number p. Okay. And they announce the prime number p. So it goes over the public channel as well. And this prime number is really a large prime number. 400 digits long, 500 digits long, 300 digits long, so large prime number p. And they announce this over the public channel. So it's known to Alice, Bob, and it might also be known to Eve. Then they pick up a primitive root, mod p, some g of that p. And they also announce this. So P and G are now known to Alice and Bob, and they share the same P, the same G, and it might also be thrown out on and broadcast on a public channel, so it's susceptible to eavesdropping. It can be intercepted, in other words. See? Now Alice, what Alice does is Alice picks some A, which is above 2 or above, and less than p minus 1. So it can't be p minus 1 and it can't be 1, because if it were, because what Alice needs to do is that he would need to create g raised to power a mod p. So this a has to be less than p minus 1, because if it were p minus 1, then the answer is simply 1, which is this. This is just trivial here. This is a trivial result. right? Mod p. This is trivial and this is trivial. Okay? So Alice chooses some a in this range and creates this function, this number. This is going to be a number, a, capital A. Let's call this number capital A. But a, small a, is a secret with Alice. She doesn't share it with the outside world. She keeps it to herself. It's in her private custody. But G is known to everyone, P is known to everyone. And capital A is then shared with Bob over a public channel. It might be broadcast. Everyone can intercept this message, right? But this is not really the message. We're trying to generate a key here. So now this capital A, which is really a number, is shared with Bob and it goes over a public channel in which G is known and P is known, but A, small a, isn't known. And this, of course, is a number. Any message, any key, any message can be cast in terms of numbers as well. It can be codified as a number, as an integer. Just imagine that when you write on a keyboard, every letter that you type is translated into an ASCII code, for example. So everything can be a number, an integer. Now when Bob receives this message, which might have been intercepted, it's Bob receives capital A, but he doesn't know small a because he has no idea what small a is. So from capital A, it's impossible. It's not impossible, it's really hard to determine small a because the process of finding small a from capital A is really called the act of discrete logarithm. So if I take the discrete log of capital A to the base G, I will get small a mod p. But finding discrete logs is a computationally hard problem, just like factoring. So this algorithm relies on the computational complexity of certain problems. So if one did know small a, it's trivial to calculate capital A. Finding the exponent of a number is easy, it's computationally easy. It requires polynomial amount of resources. But the inverse is not true. So this algorithm, this cryptology, this cryptographic algorithm relies on the hardness of certain computational problems. Okay, so it's relying upon some mathematical underpinnings. So once this object goes to Bob, Bob can do something with capital A, right? So what Bob does is Bob chooses some b, some integer b between 2 and p minus 1, takes this a. So Bob does two things. Bob takes this capital A and exponentiates this with respect to b. Okay? And mod p. Everything is modulo p. The other thing that Bob does is, just like Alice has created her own A, what Bob does is that it takes its G, the G is shared, exponentiates this with respect to B, mod P, calls this capital B, and shares this with Alice over the public channel. So Alice gets capital B, Bob gets capital A, and each one of them, so what Alice does to the B that she's received from Bob, she takes B and exponentiates this with respect to her small a, mod P. So both of them generate the capital A, each one, Alice generates capital A, Bob generates capital B, and then they share the results. And each one of the parties then takes the result that they received from the reciprocal party and exponentiates that with respect to his or her own small little letter. Okay. Now let's see what is the structure of this thing. So let's focus our attention on this thing. AB mod P. What is A? A is GA mod P. Mod P. So this is AB mod P. This is what is in Bob's possession, what he has received from Alice, and exponentiated Alice's signal coming in from Alice with respect to his own exponent small b. Now let's try to find out what this thing is. GA mod P raised to power B. This requires a little bit of mathematics. So let's find out what is meant by GA mod P raised to power B. First of all, we would know that GA equals GA mod P plus KP, where K is some positive integer. Is this true? This is how we define modular arithmetic. Any GA, any raw number in modular arithmetic is some number of times P plus the remainder comes in and it's called GA mod P. This is how we define modular arithmetic. Now this is true, okay. Now what we need is we need GA raised to power B, right? So we have something of this kind, so we need to exponentiate anything of this kind with respect to B. So we need to put exponentiate this with respect to B. So let's exponentiate both sides with respect to B and see what happens. So GAB, a new number, must equal GA mod P plus KP raised to power B. Now how do we expand this right hand side? What do we do? Okay, is there a way to expand or simplify this further? Basic maths, maybe calculus 1 or use the binomial theorem. Right, so let's use the binomial theorem to expand this. GAB becomes GA mod P raised to power B plus combination of B, some running variable L, the first term GA mod P raised to power B minus L, K, L, P, L, with this variable L runs from 1 to B, right? This is the binomial theorem, isn't it? Okay. So this becomes GA mod P raised to power B plus summation L. This is, I think, B factorial divided by L factorial divided by B minus L factorial So these are number of combinations, right? This is a combination. It has to be an integer. This must be an integer, right? By definition. Now, Is this an integer? K is an integer, is for L is an integer. All of this is an integer here. Each of these terms is an integer. Okay. So if I take the mod with respect to B, with respect to P of both sides, what's going to happen to this term if I put a mod P with respect to it? So the second term with the summation, what is this number modulo P? 0. It must be 0 because this is some, say, 175 times PL. 175 times L multiples of P. It's divisible by P. P completely divides this term. So this is 0 and I'm left with GA mod P raised power B mod P. So this means that both sides so what Bob has done is, this is simply what is in Bob's possession. So Bob has taken this string capital A or this number capital A and exponentiated it with respect to B and found out the answer and written it in modulo P. This is this term over here. But this term is simply GAB mod P. So this term is here. This is GAB mod P. What is this equal to? So Bob creates this capital B and sends it to Alice. Alice exponentiates it with respect to A. What should this be equal to? It must be the same thing. GAB mod P. Now this number that I've written in green acts as a key. This is an identical key between Alice and Bob, and they have generated this key in their private spaces without ever sharing the key on a public channel. Now, and it's all because small a and small b were unknown to the other party. And it was unknown to the public because it was never shared. It was never communicated outside Alice's world or Bob's world. But through communication, through this two-way communication between Alice and Bob, and without sharing the inner secrets that they possess of small a and small b, they have now generated two keys that are identical. And they don't need to tell others what the key is. There is no transmission of a key between Alice and Bob. So this ensures that the key remains totally secure. It's private. So this is an example of private key cryptography in which the key only remains within the private channels. And there is two-way communication. So they agree on a key and they don't even need to tell the other what the key is because they know it's going to be the same. And this algorithm depends because one cannot unwrap small a from capital A because the computational complexity of the discrete logarithmic process, just as the computational complexity of factoring. A quantum computer can break this because a quantum computer can do a discrete log in an efficient polynomially efficient manner. Finding the discrete log is an NP hard problem. So in the classical domain, this is a really nice scheme for communication, and it makes sure that the key remains only on the private channel. The other scheme that I would just like to give a glancing look at is the RSA cryptography scheme. The RSA cryptographic scheme works on somewhat similar principle, and it uses the computational complexity associated with the factorization problem. Okay, so let's look at the RSA cryptography scheme. Any questions about Diffie-Hellman? So this cryptography scheme was first presented by Rivest, Shamir and Adelman. It was published by these guys, even though there are other claimants to the originality of this cryptography scheme as well. So in order to describe this scheme, let's use another part of the blackboard, and let's use Alice's world, Bob's world, but Bob does most of the operations here, so I'm just keeping that column a bit short. So first of all, Bob chooses two large prime numbers, P and Q. Two large primes, P and Q, and they're really large. For example, each one of them could be 200 bits long, 300 bits long, really large prime numbers. And there are algorithms to find primes, and there is a computationally efficient process called the primality test, which tests whether a number is prime or not. So when computer scientists would study this, they will keep this computational complexity at the back of their minds, and that's what a physicist who does quantum computing should also remember. So two large primes P and Q are chosen, and they remain exclusively within Bob's domain, not shared. And then Bob multiplies P and Q to generate another integer n, which of course is even a bigger integer. Okay? And then what Bob does is the following. First of all, you need to remember that the Euler phi function for n is, in our previous lecture we saw that this is equal to the product of the Euler phi functions of the two primes. Okay, and each one of these, this is equals to P minus 1, this equals Q minus 1. Now what Bob does is that he chooses an E greater than 1 and less than phi n, an integer E which is in this range, such that E has two properties. The first property is that the E is co-prime with phi n. That is, E and phi n, they do not have any common divisors besides 1. Okay, so this is the first property. The second property, of course, is that E has to be in this range. So E is chosen, an integer is chosen by Bob such that it is co-prime with P minus 1 and multiplied by Q minus 1, by, which is really phi n. Examples, let's choose examples everywhere. So this is my main general flow chart for the RSA scheme, and I'm going to put in examples over here. Suppose my P is say 11, Q is 13. So I can't use a 200-bit example here because that's beyond my human mortal capacity. So I'm just going to use simple examples, smaller numbers here. So P and Q are chosen by Bob, and he doesn't tell these chosen numbers to anyone. Then he computes N, which is 13 into 11, which I think is 230. And let's on the sidelines also write out what the Euler phi function is. कितना? कितना? 140? 143. So this is P minus 1, Q minus 1, which is 10 into 11, 10 into 12, right? 120 बनता ना? So E is chosen such that it is co-prime with 120. So let's use the smallest E. Let's go from 1, we don't want to use 1, 2 is not co-prime, 3 is not co-prime, 4, 5, 6, 7. So let's use 7. You can use another E as well, so 7. Let's use 7. Now what Bob does is, Bob shares N and E over the public channel with Alice, and therefore it goes to the rest of the world as well. Right? So it is shared on a public channel. So it's susceptible to attacks by anyone. Now when Bob does this, nothing is secret at the moment. But then Bob does something really clever. What Bob would then like to do is Bob needs to find a D which is greater than 1 and less than 5n. D is another integer which Bob has to find through some algorithm such that D is such that the product of B and E is congruent to 1 mod of phi n. Okay, so D is some other integer and Bob has to use in some algorithm, and there needs to be an efficient algorithm for that, and it does exist. It's called the extended Euclid algorithm, and you can look it up. That it does exist. It helps you find D if E is known, which satisfies this condition. There is a creepy way of writing this as well. So D, one way of writing this is D is E inverse, but this is not really the reciprocal of E. This is just a symbol mod phi n, which is P minus 1, Q minus 1. So there's an efficient algorithm that computes this D given E. This is called the modular inverse of E, and you can type this up in Mathematica as well. So if I have E equals 7, if I were to type modular inverse of 7, I'll get this D. There's an efficient algorithm for that. It's not hard. So in another way to understand this is that DE minus 1 is some product, integral product of p minus 1, q minus 1. In other words, p minus 1, q minus 1 divides dE minus 1. Right? So dE minus 1 is some multiple of p minus 1 into q minus 1. This is just a compact way of writing down this thing. So now what's at stake here? These numbers n and e form a public key. They are known to everyone. But this number d, which Bob has computed on his own, and he was able to do that because he really knows what E is. Everyone knows what E is. But he also has access to P and Q, which the world doesn't. The world doesn't know about P and Q. Why doesn't the world doesn't know about P and Q? Because they only know about N. The world knows about capital N. And factorization is a really hard problem. So knowing N, there is no classical computer that can solve for the prime factors of capital N in a finite expanse of the lifetime of the universe, perhaps, if N is really large. So this computational complexity associated with factorization is at play here, is being exploited here in the RSA cryptosystem. So what Bob has now done is that Bob also has D, everyone has E, and what Bob then does is nothing, he just waits. Alice wants to send out some message to Bob. So she picks up her message, P, let's call that message M. Okay? So this is now Alice's world. Alice's message, the plain text that she wants to send out is M. It is codified in a number. And that number is such that M is less than N, or greater than 1. So M is within N. M has to be smaller than N. Now when this M comes, what Alice can do, she knows what small e is, right? Because everyone knows what small e is. Even though Bob has chosen E, but Alice knows about E because it was shared and broadcast. So what Alice does is that she takes her message that she wants to send and she enciphers it or encodes it or encrypts it. What she does is that she takes her M, exponentiates this with respect to E, and takes everything is mod capital N now. This becomes her ciphertext, the encrypted message. That's why this E is E, because it's an encryption exponent. She encrypts her message with E, even though that E has been inherited from Bob. She uses that to encrypt her message. And then she would send this over to Bob. The message goes over to Bob over a public channel. Yes. Sorry? M is some number. So suppose she wants to say the weather is lovely. So they might have decided, Alice and Bob might have decided that they want to use the ASCII code for each of the alphanumeric characters. P is some code, H is some code. So she puts her message in a number. That number has to be smaller than capital N. It's a big number anyway, which is broadcast. So she puts that number within her allocated size, makes it into a number, and then she exponentiates it with the encryption coefficient E and sends it over to Bob, and the other people can also intercept it. Now it's really hard for anyone else to recover M from C because of the hardness of the discrete log problem And because no one knows what D is, because no one knows what P and Q are, if one would know D, so when this message gets back to Bob, what he does cleverly, he takes this C and he would like to extract M from it. So what he does, he takes this C and exponentiates this with respect to D. D is only known to Bob. So Bob possesses that private key. D is kind of a private decryption key, which only he possesses. So the key has two parts. It has a part which is E, which is public, and a part that is private, D. So this is public-private key distribution system. Some of it is public, some of it is private. G.
He knows D because he knows P minus 1 Q minus 1.
Because he knows P and he knows Q. Anyone who would be able to factorize N would be able to do this decryption. But since that's a really hard problem, that's what the inherent assumption in RSA is, that prime factorization is NP hard. No one can do this unless you have a quantum computer who could do a Shor's factoring algorithm to find out these prime factors. So once C arrives with Bob, he exponentiates it with the so-called, now you know why it is D, the decryption coefficient, and he would do ME mod N raised to power D, right? So this is M raised to power ED mod N, everything is mod N. Let's see what is M raised to power ED. So M ED is, right? So the power is 1 plus some integer L, P minus 1, Q minus 1, right? Here, from here. This translates to this. ED becomes this. This is ED. So I've just expanded ED in terms of what it really means. Correct? Now this means M multiplied by M some integer like P minus 1 raised to power some integer L Q minus 1. Okay? Now everything is modulo n, capital N. By the way, what is this thing over here? This is some number less than n raised to power p minus 1. What is this number in modulo n? For Math's-Little theorem, this one, this thing, it's 1. So this number is 1. So 1 raised to power anything is, so this becomes M. So MED mod of N becomes M mod of N. But M is less than N anyway, isn't it? So this is really nothing but M. Hence, see the encrypted message that has come in from Alice, the cipher that has come in from Alice is exponentiated through the decryption coefficient by Bob, and he fully recovers the message M. Okay, so let's look at our example here. So if I were to find D from this E, mod of everything now is mod of 143. Sorry, mod of 120. So D equals the modular inverse of 7. This is not 1 over 7, this is the modular inverse of 7, mod of 120. And I did this before coming to class. This number is 103. Okay? What this really means that if I were to take 103 times my 103 times 7 DE, subtract 1 from this, this will be an exact multiple of 120. That's what this means, right? So this is just writing in English language this number theoretic congruency. So can you just verify this, please? So this is 721 minus 1 is 720. It's a multiple of 120. Now all of this is looking really simple, but in actuality, when you really want to do cryptography in a practical system, you really want big N's, big N's, big P's, big Q's. So you find D, and then Alice knows E. So suppose Alice wants to send out some message, say, which is smaller than N, our capital N is 143. Suppose she wants to send out a message 137. So she has the lazy fox is jumping over the bushes, and she converts this to a number 137. And then what she does is she takes this 137, exponentiates this with respect to 7, modulo my n, which is, I always forget, 143. Now this is with modulo n, not modulo phi n. So now this is a really big exponent. But there are efficient ways of doing this as well. There is a square and multiply algorithm, very easy to understand, which gives you a computationally easy and a polynomially scaling algorithm for finding the exponents of numbers. This is not a computationally hard thing. There is an algorithm to do this. What you do is you convert this 7 into a string of zeros and ones, and depending on whether it's 1 or 0, you just take this number and square it or square and multiply this and add all the numbers together. So look it up, square and multiply algorithm. So this is an efficient way to achieve this. So once this number is generated, this turns out to be some number. Finally it goes back to Bob. Bob exponentiates this with respect to his 103. Takes the mod with respect to n, which is 143. So all of this is done, and there's a computation. None of these steps is hard. It's computationally easy. The big O is of this algorithm is n. It scales as n. It's computationally easy. So once all of this is done, the final result will be 137. Really nice. So this is how the RSA crypto scheme works. And it relies on the computational complexity of finding the prime factors of a large integer. The integer, of course, has to be odd by definition, right? So now before we enter into the next class and we look at all of this from a quantum perspective, how does quantum information solve all of this? Because if you had a quantum computer, you could find out the factors and the RSA crypto system will crumble in front of our eyes. Just fall down. Luckily, we have never built such a big quantum computer to be able to do this at the moment. And we don't know whether we'll be able to do this. Probably the likes of Abdullah and others can achieve this in the next 10, 15 years. But right now, we don't have this technology with us. But if we had, fundamentally it's possible with a quantum computer to have the RSA crypto system walk out of the door. Now, before we enter in our next class, what I would like you to understand is, just keep one thing in mind, is that if I have some density operator rho and I want to find out the expectation value of an observable, say sigma x, the expectation value of sigma x would be given by the trace of the product of rho and sigma x. So this means if I have an input quantum state rho and somehow I am measuring sigma x, which means I am looking at the projection on eigenstates of sigma x, which are 0 plus 1, if I am talking a single qubit, 0 plus 1 and 0 minus 1, then I will get certain eigenvalues as my output. The average of those eigenvalues given some rho is given by this number. And I would also like to ask you, if I have an entangled state, say of 2 qubits, say 0, 0, 0 plus 1, 1, this state is written in some basis, in the computational basis. What if I were to write this state in another basis? So there are infinite possibilities of basis. Suppose I use a new basis in which my basis states are using notation from quantum mechanics. One of them is right, let's call this get plus, and let's call the other basis state, which is orthogonal to this basis state, so if I were to write this Bell state, which has now been written in the computational basis, in the Zeeman basis, in another basis, what would this state? Will the state still be entangled? Right? The state, first of all, entanglement is a physical property. Physics reigns supreme over mathematics, remember this. Because physics is the real world. Entanglement is a physical property. Therefore, it doesn't depend upon what basis you would like to choose. This is just for our convenience, it's for mathematical convenience. Right? If mathematics were true in a sense, then most of quantum computing wouldn't work, right? And superposition wouldn't exist, measurement wouldn't exist the way it does. Because there's no mathematical description for superposition, right? Now, if you transform the basis, entanglement would still be preserved, right? Transformation is a unitary operator. It's a rotation. So if I have some operator psi, a basis change is represented by some unitary operator, isn't it? This gives me some new state. New representation. The physical state doesn't change. It's a new physical representation. Likewise, entanglement should still be preserved if we change the basis. It's a different perspective of looking at the state. Therefore, an entangled state will remain an entangled state in another basis. And so if I were to write this, so look up your notes from basic quantum mechanics and understand how this transformation could be done. For this transformation, you need to find out this matrix. This is a basis transformation matrix in which the columns will simply be these eigenvectors. right? So this U will be, that's what this U is going to be. So if you take this U and act it upon ket 0 and ket 1 and do it for both qubits, you'll still get a new state, and that new state is going to just look like this. That's it. Still entangled. Alright, so entanglement does not depend upon the basis. However, is there a way to distinguish between states? And so this is the question that you really need to be well equipped with in your understanding. And this is all coming from basic quantum mechanics, and we've already seen many of these concepts in our previous lectures. So the next two lectures that are the vestiges of this course, the last two lectures, they're going to deal with, we're going to look at quantum key distribution and connect with some of the properties of information and entropy. So we have, unfortunately, we are not able to cover physical implementation, something which I really enjoy. How do we implement all of this? Using superconductors, superconducting qubits, or photons, or the real what you do in the lab, which I enjoy doing and I enjoy studying. But at least we'll be able to cover in the next two lectures the different communication, quantum communication algorithms. So far, we do not have any quantum channel. There are no qubits that are being shared between Alice and Bob. It's all classical information. But what happens when quantum states and quantum information enters the picture? Thank you very much.